Good morning, everyone. It's with a heavy heart that I welcome you back here to Organic Chemistry 1, our final lecture of the summer session. It's been a great pleasure and honor teaching you guys this summer. You've done very well, and I uh, am saddened that this is our final lecture. On that note, though, I would like to say that this lecture will be somewhat long because it's about alcohols. It's really the only new material that will be on the final exam because if you've already seen yesterday's exam, yesterday's lecture on synthesis, notice that it is mostly a review of all the reactions that we've learned in past chapters, and they're all just coming together to make a multi-step synthesis. So really, the final, the only thing that's going to be new in the final is going to be the alcohol information, and there won't be that much stuff about the alcohols on the final. But that being said, you need to know this material for future endeavors, classes and such. So I will do my due diligence in giving you an alcohol lecture. So just a reminder though, your final exam is on Thursday. There won't be any new material tomorrow. So you can use that day to study or relax or play video games, do something to prep you for the final exam. Today, though, there will be a quiz, and there will also be a quiz on the previous lecture on synthesis, which is just, like I said, mostly review of all the previous lectures. And then also alcohols assignment as well. So make sure you do those. They'll be posted and they'll be due by 8 a.m. tomorrow morning. And then also don't forget that your very last lab, your very last lab assignment is assigned today. The SN2 reaction of Nerolin, I believe. And so make sure you do that. That's also going to be due tomorrow as well. But again, nothing will be assigned tomorrow. No new information, nothing will be assigned tomorrow. Just remember, though, that, like I said, your final exam and lecture is on Thursday, and your lab final is on Thursday. Don't forget to do either one of those because they are not droppable and they are worth a lot of your points in the final average. Okay. All right. So I'll be around all day today and Wednesday as well. If you have time, by the way, on Wednesday. Since there's no new information, make sure you do your course evaluations. I really would like to know how I'm doing as your instructor here in Organic Chemistry 1. And also, so does my boss. So, feel free to fill out a course evaluation in the it's one of those headings, links that's in Blackboard on the menu, right, for this class. So yeah, if it suits you, feel free to fill out an evaluation and tell me how I did this semester, or this summer session rather. Whew, all right, let's go ahead and get started. Our very last lecture here in Organic 1. And it will be about alcohols and phenols, chapter or lecture 17. Let me switch over to the correct view. There we go, lecture 17, alcohols and phenols. Okay. So alcohols possess a hydroxyl group. You've heard me actually say that before. I use alcohols and hydroxyl like interchangeably, right? So, and you already know all about ethanol, and you already know about cyclopentanol. But I guess the thing to know here, though, is that if there's a hydroxyl in it or an alcohol in it, we always end it with an "ol," right? There's some extremely common natural compounds that have alcohols in them. Here's grandisol, which is a sex pheromone of the male boll weevil. Interesting, very interesting. And then we have a very important compound, chloramphenicol, and that's an antibiotic, right? We actually use antibiotic a lot in molecular biology. Antibiotics a lot. We do use a lot of antibiotics, but specifically we use a lot of chloramphenicol in molecular biology to screen out mutant genes and stuff. So it's actually kind of interesting. Oh, isolated from the Streptomyces venezuelae bacterium, potent against thyroid fever. I actually did not know that. That's very interesting. Here I am with a jar of chloramphenicol in my lab fridge, right? Not in pill form either, like powder, and I had no idea that it was used for thyroid fever. Very interesting. So Phenols, right, possess hydroxyl groups that are directly attached to a benzene ring, and you've heard me talk about phenol before as well. Um, if you haven't taken any like super, molecular biology class type of things before, we actually use uh, uh, phenol with chloroform to do DNA extraction, right? We use it to do DNA extraction, so that's pretty cool. So there's a phenol and dopamine, right? There's a phenol and dopamine. There's also a phenol in uroshiles. I don't even know what that is. Uroshiles, present in the leaves of poison ivy and poison oak, causes skin irritation. Oh my god, that's what that was when I was mowing my Serengeti of the lawn yesterday. It was ur, ur, uroshiles, or uroshiles. If anyone knows how to pronounce that, put it down in the comments below if you're watching this on YouTube. Oh, and one of my favorites, capsaicin, has a phenol in it too. Uh, I love spicy food. I am Asian after all, and so yeah, that's pretty cool. That phenol there. That's probably why drinking water doesn't help much with uh, spicy food, but drinking milk does. Because it has this fatty acid chain here, milks have fats in it and fatty acids in it, so it helps dissolve it and wash it away. And then we have THC. I've talked about THC before because my girlfriend's a drug chemist, right? And she's always doing some kind of drug chemistry forensics at her job. And THC stands for tetrahydrocannabinol, and it is a psychoactive drug found in cannabis. Cool stuff. Who would have thought that there was a phenol in your marijuana that you've been smoking, right? Not you personally, but you like in general, right? So, as always, when we start a new type of molecule, or not type of molecule, but functional group, we always have to learn how to name them, right? Alcohols are named using the same procedure as in Chapter 4 to name all alkanes, but with minor modifications. The biggest one here meaning all. You add the suffix all to the end of it all, right? So identify the parent chain, which includes the carbon that has the alcohol attached to it. Identify the name of the substituent, and then assign the locant to each substituent, giving the carbon with the alcohol attached to the lowest number possible. List the numbered substituents before the parent name in alphabetical order. Ignore prefixes except for the iso, like from the isopropanol. When in ordering alphabetically, the OH locant is placed just before or the parent name or just before the ol. Which again, I hate it when they do that. Like pent 5 all or something. Ugh, I don't hate that. Or pent 1 all. I don't like that. Just put it before the parent name. So, just so you're aware, it is storming at my house right now, so my little poop stain Kovu might try to jump in my lap while we're doing the lecture today. If that happens, just ignore it. Keep on trucking with the lecture, okay? So, next, assigned a locant to each of the substituents, right? A prefix if necessary. Give the carbon that has the OH on it the lowest number, okay? So here, of course, we're not going to give the OH the 6, because that actually is the highest number, right? So it would be correct to name it this way: 1, 2, 3, 4, 5, 6, 7, with the OH hydroxyl at 2. So we also have a alkene here at 6. So I would surmise that we name this molecule 5-dimethyl hep 6-ene-2-all. It gets a little complicated when there's a lot of functional groups inside of one molecule, but we can keep track, right? So then the locant is placed, the OH locant is placed just before or the parent name or just before the ol suffix, right? So here we have a pentanol with a OH hydroxyl on the third carbon. So that could be either 3-pentanol or pentan 3-all, which sounds really stupid. So I would go with 3-pentanol, unless there's more than one functional group that you have to denote where it is. So for cyclic alcohols, the OH group is always carbon 1. So here's cyclopentanol right there. And then for here we have R33 dimethylcyclopentanol. The methyl groups are on the third carbon there, and then the alcohol hydroxyl group is on the first carbon. Okay. So there are some common names for some very frequently used alcohols. Of course, isopropyl alcohol. We use that to disinfect ourselves during COVID, right? There's tert-butanol right there, or well, they call it tert-butyl alcohol, but I call it tert-butanol. Works just the same. Or you could do 2-methyl-2-propanol, and then this is benzyl alcohol, or methylbenzenol, phenylmethanol right here. Okay, so those are some common names that are frequently used. Just like halides, alcohols are often classified by the type of carbon they are attached to. So we have a primary alcohol here, we have a secondary alcohol here, and we have a tertiary alcohol here. And just to remind you, the primary part means 1 R group, secondary 2 R groups, excuse me, tertiary 3 R groups, right? When an OH is attached to a benzene ring, the parent name is phenol, and I've told you that before too. We use phenol in chloroform phenol DNA extractions. Okay, so an example here would be 2-chloro-2-nitrophenol. Okay, so practice of skill builder 12.1 in naming alcohols. So there's some important alcohols to discuss, like methanol, and I don't know why it only says methanol up there. That must be a typo, because there are 3 alcohols here, right? We have methanol. It's the simplest alcohol. With a suitable catalyst, about 2 billion gallons of methanol is made in industry from a year from CO2 and hydrogen gas. Wow, that's a lot of methanol. Excuse me. And you've seen us use methanol before in organic chemistry as like a solvent, right? Then there's ethanol, which is produced by fermentation of grains and fruits, right? Like when I'm distilling my own vodka using bacon. Well, actually, I guess it's using fruits there, but you can put bacon in there, you can buy what is it called, brown sugar bacon. Throw that stuff into the pot and do some distillation, man. That's some good vodka right there. I am not condoning or suggesting that you ever distill your own vodka, but I'm just saying that's interesting stuff. Okay. Industrially, ethanol is made via acid catalyzed hydration of ethylene. 5 billion gallons a year in the U.S. alone. Holy mother, that's a lot. I wouldn't drink that though. Okay, I wouldn't drink anything that has ethylene in it, or at one point had ethylene in it. Isopropanol, of course, is rubbing alcohol. That's made by industrially. That's made industrially from acid catalyzed hydration of propylene. Interesting stuff. So there's some interesting trends with alcohols, right? So the OH of an alcohol has a big effect on the physical properties of its alkyl group, right? And so or the alkane that it's attached to, excuse me. And so compare the boiling points below. If you see here, we have ethane, which is the boiling point of negative 89 degrees Celsius. Man, that is like, it's a vapor, right? And then there's chloroethane, which has a boiling point of 12 degrees Celsius, right? That's still pretty cold. But ethanol, though, has a boiling point of 78 degrees Celsius. Oh my gosh, it is 78 degrees Celsius. Remember we were doing the distillation lab a few weeks ago, or a few days ago, or however long it was ago? I say a few weeks ago, but it's only a month-long class. But I couldn't remember what the ethanol boiling point was. I said it was like 74 or 78 degrees. I was right. It was 78 degrees, man. That's in there somewhere. It's in there somewhere. Alcohols have a much higher boiling point due to the hydrogen bonding, right? We know that the hydrogen there is attached to the oxygen, which is an electronegative group, which allows for a good amount of hydrogen bonding. Alcohols with 3 carbons or less are miscible in water, right? Which makes sense because it has a hydrophilic region there and a hydrophobic region there. But the more hydrophobic region you have, the more it overpowers the solubility, the ability of being soluble in water, right? So alcohols with large carbon chains do not readily mix with water, right? So this is a 1, 2, 3, 4, 5, 6, 7, 8. That's an octanol. That's definitely not going to be miscible in water. Too much, too many hydrocarbons, right? Too much hydrophobic effect there. A strong base is necessary to deprotonate an alcohol. So sodium hydride, right, which is this mother right here. You end up with a sodium plus and then a negative hydrogen, right, which is a hydrogen with an electron, right? So that's a hydride. It can be used to often generate the corresponding alkoxide, right? So Here we have an ethanol. Oh, I didn't even realize they drew it down there already, right? So comes over, deprotonates that in acid-base function, right? And then the bond between the hydrogen and the oxygen goes to the oxygen, right? And it leaves us with this negatively charged oxygen, which is called the excuse me, which is called the alkoxide. And so now we have sodium oxide, sodium ethoxide, and then we actually get hydrogen gas from the combination of these two guys right here, right? Hydrogen gas, okay? And so the gas just floats away, and it's not there anymore, which is the reason why this arrow is not reversible. It's only going in one direction. That's because once hydrogen gas is gone, it won't be able to go back to being ethanol and sodium hydride. Sodium, potassium, lithium are often used as well, right? So here's sodium, it can do it as well, and then we get hydrogen gas again. Practical conceptual checkpoint 12.4. Okay, so the leader of the Autori here helps us again by indicating to us the stability of an alkoxide, which is formed when we deprotonated the alcohol in the previous slide with a hydride, right? Turns out that based on Ario, the leader of Autori, alcohols are actually very stable, right? As a lone pair, very, very stable, right? Right next to halides, right? And so just remember that when you're talking about these the stabilities, right, of these conjugate bases and how strong they are as an acid, in retrospect, right, those ionic acids, right, were between -10 and 3 pKa, right, the sulfuric acids and the hydrochloric acids. But right after that, we have our alcohol with 15 to 18, and then the amide, not to be confused with the amide functional group, 35 to 40, and then the pK of those alkyl groups, protons, right, 45 and 50. So they're not very acidic at all. So comparative wise, an alcohol is kind of acidic based on the Autori, right? So why is that, right? So recall the factors that affect acidity in alcohols and phenols, right? The resonance, right? The R in Ario, right? Phenol is millions of times more acidic because the conjugate base phenoxide is resonance stabilized, right? So here's cyclohexanol, has a pK of 18, which is okay, right? But phenol has even a better pK, making it even more acidic at a pK of 10. Why is that? It's because this alcohol here, right, the lone pairs on the oxygen are resonance stabilized. So it can be happier losing its proton, right? Here we go. Those electrons come down here, makes this bond go to here, right, to that carbon ion right there. That carbon ion comes down here, and then this bond goes and forms another carbon ion there. This carbon ion comes down and forms a double bond there, and this double bond forms that carbon ion there, and then we start all over again when this carbon ion forms a double bond there, and then those electrons get returned back to the oxygen, and so we're back to our original structure. Okay, we're back to our original structure. So that's why an alcohol is actually more acidic than just a regular cyclohexanol. Okay. Also, we have induction. Okay. The presence of electron withdrawing groups increases the acidity of an alcohol or the phenol, right? So here we have ethanol with a pK of 16, but if we have dichloroethanol, right, its pK is 12.2. And why is that? It's because these chlorines here, right, are doing some electron withdrawing electron density towards that direction, right? Towards that direction. And so that makes it even more capable of making that proton fall off. Okay? And then we also have solvation effects, right? The more poorly solvated a conjugate base is, the less stable it is. And the less acidic the conjugate acid is, right? Its conjugate acid is. So again, we look at ethanol here. It's a pKa of 16. And then we have terbutanol here, which has a pK of 18. Why is that? Well, if you take a look at it, look at the conjugate base of ethanol, which is ethoxide. You can have solvent molecules all around there solvating that oxygen, right? Stabilizing it. But on terbutoxide, let me make it full for you to see. There we go. On terbutoxide, the solvent molecules are incapable, of surrounding that much of the alkoxide, right? Because of all the steric hindrance coming from these methyl groups, right? And that's what accounts for the increased acidity of ethanol over terbutanol, right? Good stuff, right? Good stuff. Let me bring myself back. There we go. alcohols can be synthesized from alkyl halides via substitution, right? And we knew this already. We did this in the previous sections, but we'll do it again here, right? We have an alcohol here with an alkyl, with an halide. Excuse me. We have an alkyl halide here, right? And we can do a substitution reaction, right, and get an alcohol, right? So here's a primary alkyl halide with some sodium hydroxide. We go through an SN2 reaction and we'll get an alcohol and sodium chloride, right? Or we can have a tertiary halide here with some water, right? Do another substitution reaction. This is SN1, right? This SN1, and then we'll get the alcohol in hydrochloric gas acid or hydrogen chloride gas. So this is all stuff we've talked about before with SN1, SN2 substitution reactions, right? Alcohols can be synthesized from alkenes via addition reactions too, and we've talked about that already before, right? You can take this alkene right here, dilute H2SO4, and you'll get this alcohol. Remember that this is the acid catalyzed hydration from section 9.4. Then you can also use the mercury, right, and water and sodium borohydride, right? This is the oxymercuration demercuration from section 9.5, another alcohol right there, right? Another alcohol, secondary. Or we can use the borane, or I like to call it boron trihydride, with tetrahydrofuran, hydrogen peroxide, and sodium hydroxide. Get the primary alcohol here in section 9.6, the hydroboration oxidation reaction. So these are all reactions that you've done before, right, to prepare or synthesize an alcohol, right? So just recall that an acid catalyzed hydration will yield a Markov-Markov addition. A hydroboration oxidation yields an anti-Markov-Markov addition, right? Remember what that means, right? Markov-Markov addition is when it gets substituted at the most substituted carbon, and then the anti-Markov-Markov one, right, addition is going to be where it gets substituted at the least substituted carbon, okay? Practice that with checkpoint 12.7 and 12.8 in Wiley+. You can also convert a carbonyl to an alcohol, but it requires a reducing agent, right? And so the reducing agent is then oxidized in the process while the substrate, the carbonyl, is reduced. The reduction of carbonyl overall results in the addition of H's across the double bond, right? Which makes sense, right? There's a proton here now and a proton there now, or hydrogen there now, right? Whereas before over here, right, those weren't there, right? So that's why it's a reduction, because you're actually adding electrons to the carbonyl in the form of hydrogen atoms, right? So there are three reducing agents that can be used, right? In catalytic hydrogenation, of course, we can always use hydrogen gas in a catalyst like platinum, palladium, or nickel. My favorite is platinum, of course, and we'll get 95% of the cyclopentanol, right? This method is rarely used, though. High temperature and pressure is required, so it takes more, effort. You could also use sodium borohydride, also another common reducing agent for aldehydes and ketones. Sodium borohydride in methanol, ethanol, or water will give you 90% of the cyclopentanol. So there's a mechanism for the sodium borohydride, and the source is the hydride ion, right, which does the nucleophilic addition of the carbonyl carbon, as followed by a proton transfer from the solvent. So here's sodium borohydride, okay, and then the hydride can come off of the boron and do a nucleophilic attack on that carbonyl carbon. Okay, pushing up the electrons from that double bond, from that pi bond into the oxygen, right? Giving you the alkoxide. The alkoxide now can do a non-nucleophilic attack, but can deprotonate another proton, right, from another alcohol, and then you get the secondary alcohol. Okay, good stuff, right? Because the hydride is there, that's where that is, right? And then the proton that follows it is from there, and that's how you get the secondary alcohol. When there's an unsymmetrical ketone, when there's an unsymmetrical ketone is reduced, a chiral center is created, and a pair of stereoisomers is obtained, right? So here's sodium borohydride with a methanol, and you get the enantiomers of this secondary alcohol. The reason why you can get the enantiomers of that secondary alcohol is because the nucleophile can attack on both sides. It can do a backside attack, or it can even attack from the front side, right? There's no big old halide there blocking the way, okay? You can also do lithium aluminum hydride, right? Lithium aluminum hydride, that's another common reducing agent for carbonyl compounds. So here we have an aldehyde here. And then with lithium aluminum hydride, which is usually abbreviated as LAH, right? You get 86% of this 1, 2, 3, 4, 5, 6, 7 heptanol right here. Okay. I used a lot of lithium aluminum hydride when I was in the lab. So there's lithium aluminum hydride, there's sodium borohydride, they're structurally similar. Hydride reagents, you can see here, right? There's 4 hydrides on the sodium borohydride there, and then there's 4 hydrides there on the lithium aluminum hydride, right? But LAH is much more reactive than sodium borohydride. So lithium, as I said before, lithium aluminum hydride is much more reactive and cannot be used in the presence of a protic solvent. But the proton source, H2O, has been added after the carbonyl is reduced, right? So here we have our lithium aluminum hydride. When the hydride comes over, does a nucleophilic attack on the carbonyl carbon. Electrons from the pi bond come up, go into the oxygen, giving you the alkoxide. The alkoxide can then go and deprotonate this hydronium ion, giving you the alcohol. Okay? And some water. So hydride delivery agents are selective for carbonyl groups, whereas hydrogenation is not. Okay? So what does that mean? That means over here, if we use because we have this alkene here and this carbonyl, right? And we use hydrogenation reactions, right? Which is hydrogen gas in a palladium or platinum catalyst, we get everything reduced, right? We get the carbonyl reduced and we get the alkene reduced 90 to 95% of the time. But if we use something like sodium borohydride or lithium aluminum hydride, we can get only the carbonyl reduced to an alcohol. Catalytic hydrogenation reduces the carbonyl and the alkene, which is what I just said. The reactivity of hydride delivery agents can be fine-tuned by using derivatives with varying R groups, right? So here we have basically lithium aluminum hydride, except there's only 1 hydride there and then 3 alkyl groups. Okay? Same thing here with the sodium borohydride with 3 alkyl groups, right? These can be alkoxides, cyanos, they sterically hinder groups. So LAH, or lithium aluminum hydride, is strong enough to reduce esters and carboxylic acids, whereas sodium borohydrate is generally not, right? So here we have a carboxylic acid. With excess LAH, we can reduce this entire thing right here down to an alcohol, right? But, then also here too, same thing. Lithium aluminum hydride with some water there, with this ester, right? And we'll get the alcohol there, right, and the methanol. Reductions of carboxylic acids and esters yield primary alcohols, right, and there's your primary alcohols. So, reduction of esters require two equivalents of hydrides, right? The first step results in the formation of an aldehyde, which is then reduced to alcohol as previously discussed. And I apologize for this being so small. This is even really small on my slide. I should have made this bigger, right? But we'll do our same old nucleophilic attack with the hydride here, right, into the carbonyl carbon of the methyl ester, right? And then electrons from the pi bond go up into the oxygen, making the alkoxide. Alkoxide electrons come back down, right? They come back down, reforming the double bond. And then what happens then is that we have the methoxide leaving group leaves. Okay, and then another hydride can come over again, do another nucleophilic attack on the carbonyl carbon. Pi bond electrons go up into the oxygen, forming the alkoxide again. But this time the alkoxide does does a proton transfer, right? It deprotonates the proton off of hydronium ion, right, giving you some water. And then you'll get your primary alcohol. Okay? Methoxide is not a good leaving group, but acts like one here because the high energy intermediate becomes a stable aldehyde. So practice this with Skill Builder 12.4, drawing the mechanism. So diols are named using the same method as alcohols, except the E is dropped from the alkane name, and the suffix is diol. the suffix diol is used. So here we have two alcohols, right, on either side of this alkane. 1, 2, 3. That's a propane. So that's a 1,3-propodiol. Okay. Here we have two alcohols here, right, and the we're numbering it from 1, 2, 3, 4, 5, 6, right? So this is a 1,5-hexadiol, right? The term glycol is also used to describe an alcohol compound with two hydroxyl groups, right? So that's a glycol. So let me show you that real quick there. So here we have ethylene glycol, right, which is an ethane with two alcohols on either end. Okay, two alcohols on either end. Diols can be prepared from the reduction of diketones, right? So we have two ketones here. We can shoot some hydrogen gas at it and some palladium. It will reduce it down to an alcohol. Also do it with lithium aluminum hydride, and also you can do it with sodium borohydride. Then we'll get our diol here. So recall in chapter 8 when we discussed how to turn an alkene into a diol, right? So here we have cyclohexene, okay? And we can use a peroxy acetic acid along with some hydronium ion here to make an anti-dihydroxylation. If you recall, that was from chapter 8, section 11, right? Or section 1.1. Before we move on from that one, I just want to remind you too, another peroxy acetic acid you can use is called MCPBA, right? And that's metachloroperoxybenzoic acid, right? And that structure, if you were wondering, of MCPBA looks like this. Right? And that can also be used in the anti-dihydroxylation reaction as well as the peroxy acetic acid that you're using here, right? If you wanted to do a syn dihydroxylation here from section 8.12, recall that you can just use a catalytic amount of osmium tetroxide along with some NMO, and you will indeed get that syn dihydroxylation right there. You can also use Grignard reagents too to synthesize alcohol. And a Grignard reagent is basically an alkyl halide treated with magnesium metal. So here we have our alkyl halide, we add in some magnesium metal, and we get the magnesium between the alkyl and the halide, right? So here we have a bromobenzene, and we add in some magnesium, and now we have the magnesium between the benzene and the bromine. Or we can also do it with this 1-chloro-propane, and add in some magnesium there, and then we'll get the magnesium inserted between the chlorine and the propane. Let me move my head so you can see that real quick. There we go. Okay. So let's talk about the electronegativity real quick of Grignard reagents. Right, the electronegativity difference between the carbon, which is 2.5, and the magnesium, which is 1.5, is great enough that the bond is significantly ionic in character, right? And so what that means then is that this magnesium benzene here, right, it acts like an ionic compound, right? And it's Grignard. That's why Grignard reagents are so helpful, right? So now you have basically an anion, in the form of the benzene ring, and then you have in magnesium bromide there we have a cation. Okay, the carbon atom behaves like a carbon anion and is a strong nucleophile, as well as being a very, very strong base. Oh, I forgot to bring myself back. Makes it a really strong base, right? So we can do a lot of chemistry with a Grignard reagent. Grignard reagents act like LAH as a strong base and will attack strong nucleophile, and will attack a carbonyl group of a ketone or an aldehyde. So here we are. We have our Grignard reagent. It's probably that benzene ring with that has the carbon anion, right? It'll come over and do a nucleophilic attack right there on that carbonyl carbon of the ketone, right, and forming the alkoxide. And then the alkoxide will come over and deprotonate hydronium, giving you the tertiary alcohol, right? The key difference, right, is that Grignards will give a new carbon-carbon bond, right? Grignards will give a new carbon-carbon bond. And that's because that Grignard right there came from an alkyl to begin with, right, from that alkyl halide, okay? So that's pretty cool. Because Grignards are both is both a strong base and a strong nucleophile, care must be taken to protect it from exposure to waters or alcohols, right? So here we have our Grignard reagent coming over and deprotonating the water, right? And then, well, the problem with that then, right, is that once it becomes protonated with that water's proton and we get this magnesium compound here, it's going to stay that way because we'll never be able to use it again. Because at that point, that proton is pretty much stuck on that alkyl, right? Because alkyl protons are not very acidic at all, right? So generally, we use anhydrous ethers as solvents for Grignard reactions and not water, because it's that whole solvating effect thing that that we were talking about before with having the solvent react with the reagent before it can react with the actual reactant that you want it to react with, right? Okay, so here's some examples using some Grignard reagents, right? We have a cyclohexanone here, and we'll use this Grignard reagent, and we'll get this alcohol here. This tertiary alcohol, I guess that would be 1, 2, 3, 4, 5, 6. So that's 1-methyl hex 1-all, right? Here we have an aldehyde. This aldehyde can also be treated with some Grignard reagent, and we'll get this secondary alcohol here, which actually turns out to be a racemic mixture, right? Because it's a chiral carbon, and 50% of it will be S, the other 50% will be R. We have a methyl ester here, also treated with some excess Grignard reagent, and we'll get a tertiary alcohol here, and also some methanol being produced. Practice with Skill Builder 12.5 in preparing an alcohol in Wiley Plus. So now that we've made all those alcohols, let's consider some issues, some challenges we have, right? Say we wanted to make a molecule, right, that will change a ketone into an alcohol, right, but also ends up with an alcohol on it too, an additional alcohol, because we form carbon-carbon bonds with a Grignard reagent, right? The problem here is that the Grignard reagent itself would have to bear an alcohol on it, and that's a problem. Why is that a problem? Because we remember Grignard reagents are actually very acidic, right? And when they're very basic, right? And when they're around a weakly acidic hydroxyl or alcohol, they can just deprotonate that alcohol, right, reacting with it before it actually reacts with the ketone to make the what we wanted to be the original reaction right there, to turn the ketone into an alcohol, right? So that with that in mind, we know then that the alcohol can act as an acid. So Grignard reagent, right, and alcohols they're incompatible in the same reaction. So how do we get this kind of reaction done? The alcohol has to be protected and prevented from reacting. Okay, so here the first step to do is to protect the alcohol, right? And now it has a protecting group on it. We'll elaborate that in a second. Okay, then we form the Grignard reagent and perform the Grignard reaction. Right, we've reduced the ketone to an alcohol with the protecting group still there, not being reacted with at all. Right, and then we deprotect the molecule, and then we get our alcohol back. Right, now we have our diol again. Not again, but now we have our diol product. So one protecting group we can use is called trimethylsilyl, or TMS, right? And the way we do that is we'll take our alcohol and we'll treat it with trimethylsilyl chloride, which is this species right here. The trimethylsilyl chloride will turn the alcohol into an ester of the trimethylsilyl, right? And that will protect the alcohol during the Grignard reaction. So interestingly enough, we're not really protecting the alcohol, we're actually removing that proton, replacing it with something else, but we can easily bring back that proton afterwards. Okay. How do we achieve this? Well, evidence suggests that the substitution at the silicon atom occurs by SN2 mechanism, and because the silicon is much larger than carbon, it is more open to backside attack, right? So here's tert-butyl chloride, right? The attack is too sterically hindered, right? That carbon is so small, it's too sterically hindered, but silicon is much bigger, and so backside attack is not sterically hindered, right? Backside attack is not sterically hindered, right? The TMS group can later then be removed with hydronium and fluoride, right? So here's our TMS ester, right? Adding in some hydronium or fluoride, and we'll get the alcohol back. TBAF is used to supply the fluoride ions, right? Tetrabutyl aluminum fluoride. Tetrabutyl aluminum fluoride. That's an interesting compound. So overall, the process is shown below, right? We'll have our bromo alcohol compound, right, whatever it may be, treated with some TMSCl, or trimethylsilyl chloride, right? to protect it, and then we got our bromo trimethylsilyl compound. We'll do our Grignard reaction, right? We'll form our Grignard reagent, and then we'll do our Grignard reaction, right? Which is here where we reduce this ketone. We reduce it down to the alcohol. We'll still have the OTMS there, right? The trimethylsilyl there. We'll deprotect it with the TBAF, right? And then we'll get our diol again. Or not again, but we'll get our diol product. Practice this with conceptual checkpoint 12.16. So 2 million tons of phenol are produced industrially yearly, right? And so we can do this where we have benzene, treat it with some alkene and phosphoric acid, not hydrophosphoric acid, but phosphoric acid. That becomes cumene. Then we'll have some oxygen there, right? Cumene becomes cumene hydrogen peroxide. Then we can do make it acidic, right? Go get our phenol and an acetone, right? And so acetone is actually a very useful byproduct. Phenol is a precursor in many chemical syntheses like pharmaceuticals, polymers, adhesives, and food preservatives. And I already told you we use phenol in chloroform phenol extraction. And acetone, right, can actually be used to do what? You can use it to remove your nail polish. Good stuff. So tertiary alcohols can be converted to alkyl halides using a halide, right? Like a hydrogen bromide, a hydrogen chloride. And so this is it's a typo right there that should say area. So here we have a tertiary halide, tertiary alcohol, and then it can do a deprotonation of the alcohol. Of the hydrogen bromide. Hydrogen bromide, the bond between the hydrogen and bromide comes to bromine, and then after that we can do the water. After that, the water can leave as a leaving group, right? And then the nucleophilic attack can be done by the bromide ion to give you a tertiary bromide. Okay. For secondaries and for primaries and secondary alcohols, the reaction occurs via SN2, right? So yeah, notice that this was an SN1 reaction, right? We had the leaving group leave first, and then we did the nucleophilic attack, right? But for primary and secondary alcohols, the reaction occurs via SN2. We can do the deprotonation once again, right? We get a bromide leaving group there, and then the bromide can come over and do a nucleophilic attack on that carbon, and then the water leaves as a leaving group, and then we get our alkyl bromide and our water. Okay. To make alkyl chlorides, zinc chloride can be used with hydrogen chloride. So here we have a propanol treated with hydrogen chloride and zinc chloride, and we'll get our 1-chloropropane. Okay. The zinc cation is required to make the OH a better leaving group. So here we have the nucleophilic attack of those electrons on the zinc. We get this zinc complex here, and then the nucleophile chloride can come over and do a nucleophilic attack on that carbon, and then the zinc chloride complex water can leave as a leaving group, leaving us with our, and let me move my head, leaving us with our 1-chloropropane. Okay, 1-chloropropane. So also recall that alcohols or hydroxyl alcohol groups can be converted into good leaving groups, such as the tosyl group, right? So here we have tosyl chloride and pyridine. We can change that alcohol, because alcohol is not a good leaving group, into the tosylate right there, right? And once you have a tosylate, you can do SN2 reaction to replace that tosylate with an alkyl, not with an alkyl halide, but with a halide. Okay. The tosylate can undergo SN2 reaction to substitute to obtain an alkyl halide, and so that's basically what happened up there. So here we have tosyl chloride with pyridine, and then we have sodium bromide, right? And we've started with an S alcohol, and we end up with an R alcohol, and we end up with an S bromine, alkyl bromine, right? So primary alcohols and secondary alcohols can also be converted into alkyl halides using thionyl chloride and Pabst Blue Ribbon. Not Pabst Blue Ribbon, but phosphorus tribromide. we can take this propanol here, treat it with some thionyl chloride and some pyridine, and we'll get our 1-chloropropane. And we can treat that same propanol with some Pabst Blue Chloride, Pabst Blue Ribbon, phosphotribromide, and we can get the 1-bromo propane. So how does the thionyl chloride mechanism work? Let's check it out here. The alcohol, right, its electrons can do a nucleophilic attack on the sulfur of the thionyl chloride, and then the pi bond electrons come up to this oxygen like so. And then in the intermediate step, right, in the intermediate step, these electrons come back down to form the pi bond, and then the chlorine leaves as a leaving group, right, as a chloride. So now the alcohol is attached to the thionyl chloride, right, and the pyridine can come over and deprotonate. The pyridine can come over and deprotonate, and then the electrons from the oxygen and the hydrogen from that proton come down, restoring that positive charge and neutral charge on the oxygen. Okay. So now we have a good leaving group attached now instead of an alcohol, right? Now it's that thionyl chloride group, and so chlorine can come over and do a nucleophilic attack on the carbon that's attached to the alcohol, right? The oxygen, and then that breaks that bond there, bringing these electrons over here to the thionyl chloride, right? And we basically restore thionyl chloride back to, we don't restore the thionyl chloride back to that, but it just makes it so that it's a good leaving group. And so we end up with our 1-chloropropane, silicon dioxide, and chloride ion. Okay, chloride ion. Then we have the Pabst Blue Ribbon mechanism. The phosphorus tribromide mechanism, right? Again, we have a bad leaving group in the form of this alcohol here, but it can do a nucleophilic attack on the phosphorus, making the bromine leave as a leaving group, as a bromide. That bromide can then come over and do a nucleophilic attack on the carbon attached to the oxygen there, and now it leaves, right? That entire complex there with the alcohol and the phosphorus dibromide this time now leaves as a good leaving group. Okay, in an SN2 reaction, we get our 1-bromo propane. Okay, practices with Skill Builder 12.6, proposing reagents. So in section 7.1, we saw that alcohols can undergo elimination in acidic conditions. So we have our tertiary alcohol here, and we treat it with some sulfuric acid and some heat, and we can turn it into the alkyne, right? The alkene, with some water, right? So the tertiary follows an SN1 mechanism under these conditions, where the alcohol will do a nucleophilic attack on the water, right? Or the hydronium, pulling off a proton. We're left with water here. And then now we have the water leaving group right there, right? Water leaves really easily, leaving us behind with a carbocation right there. And then another water can come by, deprotonate the proton right there, and then this will come back down to form the double bond, right? To fill in pi electrons and form a double bond, right? And we'll get our alkene, okay? So then also recall then that E1 elimination generally favors a more substituted alkene, right? So here we have our cyclohexanone, and with concentrated sulfuric acid and heat, we'll get a major product of either the ZZEF or the Hoffman product, right? So the less substituted alkene can only be favored via E2 elimination using a strong bulky base. Man, back to the ZZEVs and the Hoffmans and the bulky base and slender base things. So recall that. Remember that. So if an alcohol is converted to a better leaving group, then a strong base can be used to promote an E2 elimination. Okay, so here we have our tertiary alcohol, and it is being treated with tosyl chloride in some pyridine, and then we'll get our tertiary tosylate rather. Some sodium methoxide will come over, a slender base will come over in an E2 mechanism and give us our ZZEF product, right? So E2 reactions generally prefer over E1 reactions here. E2 pathway is not susceptible to rearrangements, and regional selectivity can be controlled, which is what I said before. It could either be ZZEF versus the Hoffman, right? To practice this conceptual checkpoint, 12 point, let me move that out of the way. There we go. Conceptual checkpoint 12.19 on Wiley Plus. We also saw that alcohols can be formed by reduction of a carbonyl, right? The reverse process can happen too, where an oxidation is possible. We can oxidize this alcohol and turn it back into a ketone, right? So you can go both ways. You can make it a ketone through oxidation, or you can make it an alcohol through reduction. So oxidation of primary alcohols proceed to an aldehyde and then to a carboxylic acid, right? So we always start here with a primary alcohol. We oxidize once and we'll get an aldehyde, and we'll oxidize again and we'll get a carboxylic acid. It always goes in that order. Oxidation of secondary alcohols, right, proceeds as a ketone, produces a ketone, right? So here's your secondary alcohol. We oxidize it once and we get a ketone, and that's all it can go. It can't go any further than that. So the thing I'm sorry, let me bring myself back. So the thing I want you to remember here when we're talking about oxidizing alcohols, right? Especially when we're talking about a primary alcohol, it always oxidizes in this order. It always starts out as a primary alcohol, and then you oxidize it to an aldehyde, right? And you oxidize it again to a carboxylic acid, and that's all that carbon can be oxidized to. Okay, and then for secondary alcohols, it goes from secondary alcohol to just a ketone. Okay, just remember that order. Tertiary alcohols generally do not undergo oxidation because they do not have any protons at the alpha position, right? There's no protons here, so there's no oxidation that can occur. Okay, no reaction. There is a large number of oxidizing agents that can be used to oxidize an alcohol. The most common oxidizing agent is chromic acid, and it is formed from either sodium chromate in aqueous solution, in an aqueous acid, right? Or I can't remember what that's called. Oh, it's right there. Chromium trioxide. So here's chromium trioxide. We can treat it with some acid and some acetone, and we'll get chromic acid. Or we can use sodium dichromate, right, which is this up here, and we can treat that with some acid, right, sulfuric acid and some water, and we'll get chromic acid. Okay. Sorry, I don't have all my chromium compounds memorized. So oxidation of alcohol with chromic acid involves formation of a chromate ester, and then elimination to form a pi bond, right? So here we go, stage one. We have our alcohol here, and we have our chromate ion here, right? Fast and reversible, and we get our chromate ester here, where the chromium is now attached to the alcohol, right there, right? I don't know why I drew an arrow that way. It should not be like that. So I was just trying to denote where the chromate was attached to the alcohol, and we get water. In stage two, the water can come over and do a nucleophilic attack, can do a deprotonation here, and so the bonds between the oxygen and the carbon, the hydrogen and the carbon, come over, forming a bond there, making it so that we lose the alcohol as a leaving group, and now we have a ketone and a hydronium and chromate ion. Okay. Chromic acid will also oxidize a primary alcohol to a carboxylic acid. So here we go again. We have a primary alcohol. We'll use some chromic acid, and we'll get the aldehyde. We'll use the chromic acid again, and we'll get the carboxylic acid, right? So PCC, pyridium chlorochromate, can also be used as an oxidant to produce aldehydes. Here's PCC and methylene chloride, right? And here's our primary alcohol, and we ended up getting an aldehyde from that. So pyridium chlorochromate, this is its structure right here. Okay, right here we have our pyridium, pyridinium. There we go, pyridinium, and we have our chlorochromate compound. Okay. Regardless of the oxidant used, either chromic acid or PCC will convert a secondary alcohol into a ketone. So remember that. When you have a secondary alcohol and you want to make it into a ketone, what do you use? Some kind of chromic compound, right? Either chromic acid, right? Either chromic acid, which starts out as sodium chromate and sulfuric acid, right? Or use PCC, which also has chromium in it as well, and methylene chloride, right, to get your ketone, right? And remember that in our like retrosynthetic analysis and our multi-step synthesis problems. Okay. So chromium reagents are toxic and they're horrible for the environment, which if you recall from our last lecture, we're trying to be more green about these things, be more environmental, more green chemistry, right? So a couple of alternatives have been developed for you to be able to use instead of having to use chromium reagents. One of them is used in this thing called the Sworn oxidation, okay, where we use dimethyl sulfoxide and oxyl chloride to form an active oxidant, and that active oxidant is chlorodimethyl sulfonium ion, right? And I don't really care, I don't really need you to worry about how it's made or anything like that, but this is the reagent that you need to be aware of right here, the chlorodimethyl sulfonium ion. Okay. The chlorodimethyl sulfonium ion is the active oxidant, and in the presence of the triethylamine, right, it can attack the alcohol and then form a pi bond. Okay. Again, we have a reaction here where we have the secondary alcohol coming over and doing a nucleophile attack on that sulfur of the sulfonium ion, right? And then the chloride leaves as a leaving group. Now the sulfonium ion is attached to the alcohol. The triethylamine comes over, deprotonates the proton on the oxygen, and then the electrons get restored to the oxygen. Okay. Then the triethylamine comes over again, deprotonates a proton that's on a carbon, and then that makes a carb anion. That carb anion then deprotonates the other carbon, the carbon that has that's actually attached to the alcohol from the original alcohol molecule, right? And when it deprotonates that proton there, that comes down, forms a double bond, right? And so that actually kicks off the sulfonium ion leaving group, leaving us with a ketone and DMS as a byproduct, right? So here, of course, secondary alcohols are oxidized to ketones. But the thing I really want you to remember from this slide is that chlorodimethyl sulfonium ion, right, along with ET3N, which is triethylamine, can be used to do an oxidation of alcohols, secondary alcohols, to ketones alternatively, right? So remember that, to put that in your toolbox of reagents you can use when we're doing those synthesis problems. So like PCC, the Sworn oxidation can also convert primary alcohols into aldehydes, right? So here we have a primary alcohol, and it turns into an aldehyde. But then another alternative we can use is called the Des-Martin pyridine oxidation, okay? And it yields analogous results to the Sworn oxidation, right? So here DMP is the abbreviation, primary alcohol into an aldehyde, secondary alcohol into a ketone, also a DMP, right? This is the structure of DMP, but I'm not too worried about you knowing how to make DMP. Just remember that DMP can also be used just the same way that the sulfonium ion can be used as an alternative to oxidize primary alcohols into aldehydes and secondary alcohols into ketones. Just for your reference, this is the pyridinane intermediate, right? That's the intermediate that goes through before it forms the ketone or the aldehyde. And so we get our aldehyde here, and then we get these byproducts. I don't really care much about that. Just remember, DMP can be used to oxidize alcohols, right? DMP oxidation is non-acidic and doesn't require high temps, but chromium oxidations do, and that's why DMP is used more often, more commonly. So nature also employs reducing agents and oxidizing agents too, and one of them is NADH. And if you recall back from biology class, or maybe even a cell biology class, we use NADH a lot in our bodies, right, in glycolysis and the citric acid cycle, to take electrons that we've gotten from the decomposition, the breakdown of sugar or glucose, right, and those electrons are carried by NADH, also FADH2 as well, and also NADPH, right. Those are all electron carriers, but specifically NADH here is carried to the electron transport chain, where those electrons go into the four complexes, or the three complexes from NADH anyway, the three complexes of the electron transport chain, 1, 3, and 4, and they end up being transferred to the terminal electron acceptor, oxygen. And that's all done so that we can do ATP synthesis, right? By pushing protons out into the outside of the membrane, right, where the electron transport chain is, and so they can all be funneled back through into ATP synthase to make ATP, right? So obviously, then NADH is super important in our biology. Okay. And I know I went through that very quickly with the electron transport chain and all that stuff. That's because you don't need to know it for the test. You'll learn it in biochemistry. Although it is one of my favorite topics to talk about. So we have a synthesis strategies here summary. Okay, we have alkynes. Let's start in this corner. We have alkynes, and we can use hydrogen gas and Lindlar's catalyst, right? Or even sodium in the sodium dissolving metal reduction, right? And an ammonia to make alkenes. Okay, we're bringing it all together here. Okay, these alkenes can then also be treated with hydrogen gas again, right? And platinum catalyst to make make alkanes. Okay, bring it all together. Alkanes can then be treated with bromine gas in a radical reaction to make an alkyl halide, right? Then this alkyl halide here can go through either a bulky base or a slender base through an elimination reaction to bring you back to the alkene. Okay, the alkene can then also be treated with some hydrogen bromide or hydrogen chloride with some peroxide and give you back the alkyl halide. Okay, the alkyl halide can be then treated with in an SN2 manner with sodium hydroxide or with water in an SN1 reaction and get you an alcohol. That alcohol right there can then also be reversed, right, with some hydrogen, with an halide, and then the sulfonyl. That's the remember that the sulfonium ion I was talking about with pyridine, or even Pabst Blue Ribbon. I mean, phosphorus tribromide, right? The tosylate, or even the sodium halide, right? And it can bring you back to the alkyl halide. Okay, this alcohol here can then also be treated with some concentrated sulfuric acid and heat, the tosyl chloride and pyridine, and sodium methoxide to get you back to the alkene. But this alkene can be turned into the alcohol, right, with treatment with acid, with boron trihydride and THF, or even with the mercury in the mercury mercuration demercuration reaction, right, to get you back to the alcohol. That's along with the sodium borohydride and the sodium hydroxide. Okay, this alcohol, right, can go over here using DNP or the swarm, right, or the chromate compounds or PCC to make you the ketone, right, or this ketone can be treated with a reducing agent like lithium aluminum hydride and water or sodium borohydride and get you back to the alcohol. Okay, and then an alkyne, right? An alkyne can be converted into the ketone or /aldehyde using sulfuric acid, the hydrogen peroxide, and then the so this is the diacyl borohydride, right? Diacyl borohydride, and then hydrogen peroxide and sodium hydroxide, right? Practice with Skill Builder 12.8, converting functional groups. Just a little bit more about Grignard reagents because they're so important. Recall that a Grignard reagent is a carbon-carbon bond forming reaction, okay? And these are all the reactions that we saw in our examples before, okay? Where we had our ketone here turned into the alcohol here with the new new methyl group there, right? And then we have here our aldehyde here that got reduced to the alcohol, and then we also have our new CH group there, a new methyl group there. And then we have the methyl ester here being treated with the excess Grignard reagent, and we get actually 2 methyl groups there, right? So there is no one reaction that converts an aldehyde into a ketone, but with the Grignard reaction followed by oxidation, it can be accomplished in 2, okay? Here we have our aldehyde, and attacking with the Grignard reagent, we get the alcohol and the alkyl group, and we oxidize it again, and we'll get the ketone, right? So how do we do that? We use the alkyl magnesium bromide, or the alkyl Grignard reagent, right, with some water, and then we can use the, we're not being very environmentally friendly here, but we'll use sodium dichromate, sulfuric acid, and water, and we'll get the ketone from the aldehyde, okay? So practice this with conceptual checkpoint 12.24, and skill builder 12.9, proposing a synthesis. That ends, so sad, that ends our lecture for today. That also ends our class. So I hope you enjoyed our class, and I hope you learned a lot in organic chemistry with me. Be sure to let me know how I did in the class by filling out your class evaluations. Any concerns you might have, anything, suggestions, I would love to hear them. But if you just overall enjoyed the class, you let me know that too, because then I know I'm doing something right. So this will be our last assignments for the entire summer session. So due tomorrow will be the alcohol and phenols assignment at 7:59 a.m. June 30th. Quiz 12 will also be due by then too. And then just as a reminder, you have a lab that's due by tomorrow as well, the SN2 preparation of Nerolin. And then last but not least, your final exam in lab and in lecture are on Thursday, July 1st. Okay? I'll see you again one last time, or actually 2 more times, in the pre-lab lecture for that SN2 preparation of Nerolin lab. And then also in the Quiz 12 Solutions video. But then after that, that's it. So good luck, everyone. And I'll see you around.